We're still pretty much talking about heart anatomy, but we're going to get into cardiac cycle. It's all very, very interrelated. So what we're seeing here is just the left side of the heart, considered as its own pump, right? We have contraction of the atrium, and that's going to push blood into that left ventricle. And then when that left ventricle contracts, we're going to actually close that bicuspid valve or mitral valve because of the pressure of the fluid against the cusps of that valve, and actually open that aortic semilunar valve all at the same time. So the opening and closing of the valves is something that we need to consider when we're looking at the cardiac cycle, which is really the major topic that we're coming to right now. So just to review, the epicardium, myocardium, and endocardium are the layers of the heart. The epicardium is the same as the visceral layer of the serous pericardium. The myocardium is made of cardiomyocytes, or cardiac muscle cells. The endocardium is the epithelium on the inside of the heart. You have paired atria and ventricles. You have two AV valves known as the tricuspid and the bicuspid. The bicuspid is also known as the mitral valve. You also have two semilunar valves, the pulmonary semilunar valve and the aortic semilunar valve. These all serve your two side-by-side pumps to make sure that blood only moves in one direction through the heart and does not go backwards. Here is that one direction, and here's another summary of that one direction. So if you didn't catch it when I was saying it in the last video, here's a nice summary for you. One thing I did not mention is the little path over here with the coronary arteries. So I did have you see the left and right coronary artery, and you did see the great cardiac vein and probably the middle cardiac vein. Now we do again have to oxygenate that heart tissue itself. So we're coming, that right and left coronary artery are branches off of the aorta. And then remember, we do draw all of our deoxygenated blood into that coronary sinus and back into the right atrium. So the systemic circulation looks like this. Pulmonary circulation is here. And then the coronary circulation is here. We did all this, so it's written down for you. Okay, cardiac cycle. I like the cardiac cycle. It strikes fear into the hearts of students everywhere, at least the way I do the cardiac cycle. The way I do the cardiac cycle in an A&P class, which means you don't have to deal with it just yet, is we actually have to connect the cardiac cycle to everything associated with the cardiac cycle, which is valve events, pressures, ECG readings, yeah, everything. So what do I mean by the cardiac cycle? I mean your atria contract and your ventricles contract, and there's a little dance to go with it. It's not a dance I invented. There's a video called The Living Arrhythmias, and I highly recommend that you watch it. It's on YouTube. It's from probably the 60s or 70s. It's a cardiologist, or it's made to look like it's from the 60s or 70s. It is actually, as I understand it, a cardiologist who came up with it, and he makes a little dance for the way that the heart beats, and it's very accurate. And then he also illustrates various dysrhythmias or arrhythmias with this dance. It's highly effective at teaching arrhythmias once you understand the physiology of arrhythmias, which we are not there yet. But I'm going to probably end up doing this dance a little bit, and I just want you to know what that means. First, let's define systole and diastole, and let's also make sure that you can pronounce it. It is systole and diastole. Systole, diastole, systole, diastole. I know in your heart of hearts you want it to be systole and diastole. It is not. It is systole and diastole. Now, diastole refers to relaxation of a chamber. Systole refers to contraction of a chamber. In terms of blood flow, ventricular systole is a lot more important to us than atrial systole. So atrium, when the atria contract, it just pushes any remaining blood. It's going to help us fight gravity if we're standing on our head. But in terms of getting blood flow out to your body, it's really the ventricles that are the star here. So if you're looking at a blood pressure reading and thinking diastolic, systolic, what are we talking about here, atrial or ventricular? They're talking about ventricles. So that's the default. If you just say systole without specifying atrial or ventricular systole, you're talking about ventricular systole. You would have to specify atrial systole if you were talking about atrial systole. For now, best practice, if you're talking about atrial systole, say atrial systole. If you're talking about ventricular systole, say ventricular systole. But if somebody ever says systole at you, you know they're talking about the ventricles. Now, there is a time when your entire heart is in diastole, everything's relaxed. That's called atrial and ventricular diastole. The next stage, really the first stage in my opinion, I like to start the cardiac cycle here, is atrial systole. So the atria contract first. When the atria are contracting, the atrioventricular valves, atrioventricular valves are open and the semilunar valves are closed. It's such a weird picture. Yeah, semilunar valves are up here in this illustration. Not a big fan of this illustration. I spent some time updating it. Let's use this picture. I did spend the time updating these pictures to make sure that they're the good ones from your textbook. Okay, so we start with diastole. Then we go into atrial systole. The atrioventricular valves are open. The semilunar valves are closed. We have it's actually called early ventricular systole. So while the ventricles start to contract, that's about the same time when the atria start to relax. So as the ventricles are going into systole, the atria are going into diastole. Initial ventricular systole closes the atrioventricular valves. It has to, because we are going to squeeze the heart like a tube of toothpaste. We're trying to get that blood to go towards that aorta and pulmonary trunk. So in order to get that blood towards that aorta and pulmonary trunk, we are going to need to close the AV valves so we can squeeze these chambers. And eventually, we're going to open the semilunar valves. So in late ventricular systole, we still have closed AV valves. Now we've opened both sets of semilunar valves simultaneously. Then we will begin ventricular diastole. And the first thing that's going to happen is the semilunar valves are going to close. At this point, the AV valves are still closed. But once everything is relaxed, those AV valves are actually passively open. So when we are in all relaxation, total heart diastole, atrial diastole, ventricular diastole, then the AV valves relax open. Semilunar valves are still closed at this phase. So just summary: atrial systole, ventricular systole early, ventricular systole late, ventricular diastole early, ventricular diastole, and atrial diastole late. AV valves are open, semilunar closed, AV closed, semilunar closed, AV closed, semilunar open, AV closed, semilunar closed, AV open, semilunar closed. 'Tis but a taste of what is to come. Now, your heart makes sounds throughout the cardiac cycle. One thing I want to prove to you right now is that the contraction of a muscle does not make a sound. Sound that you hear for heart sounds is nothing to do with muscle contraction. Why is this important? Because students get this wrong a lot. So go ahead and listen to your biceps brachii muscle. Does it make a sound? Does it make a lump? Does it make a dub? It does not. There's no sound coming from your biceps brachii muscle while it contracts. Maybe at the submicroscopic level, if you're just like an ion floating around in that sarcoplasm, You could hear something happening if you had ears at that level, which you don't. No muscle contraction doesn't make a sound. Cardiac muscle contraction doesn't make a sound. What makes a sound in the cardiac cycle is chambers, or not chambers, valves closing. So when your AV valves close, there's a little smack sound, right? And when your semilunar valves close, there's a little smack sound. I don't know if my mic caught those. Hopefully it did. That first sound, AV valves closing, is LUP. The second sound, semilunar valves closing, is DUP. We call those S1 and S2. Now I updated this link, so there was a link in this video. It's now down here. I went to this link and I found that website to be entirely broken. It seems to be a bit on the old side. It asks you to be on Netscape Navigator 4.0 or higher. I'm old enough to have used Netscape Navigator. I'm old enough to have used DOS as an operating system. That having been said, I think there's supposed to be audio on each of the websites that are in here, and I couldn't get any of them working. So I found this YouTube video, and this plays the audio of the heart sounds in a normal cardiac cycle, and also gives you some examples of how some heart murmurs sound. So again, if the sounds are cusps of valves closing, a heart murmur, therefore, is... Go away. Okay. A heart murmur, therefore, is something is preventing that cusp from closing the way it should. So a heart murmur means typically, some of the more common heart murmurs mean that there's some failure of the valves to close. And instead of blood moving forward through the heart into the next chamber or great vessel that it's supposed to go to, it is whooshing back into the previous chamber where it's not supposed to be. So that's what a heart murmur usually is. So again, LUP, DUP. If you hear a LUP and a DUP throughout a cardiac cycle, everything's happy, everything's good. If you hear a whoosh dub, that's a heart murmur. And if you want an example of that, that's the website where you can go to. You can try the old website. Maybe you have Netscape Navigator 4.0 and it works for you. It didn't work for me. I'm on Firefox right now. That's what I tried it on. There might be another browser that it works on. I've put us at a weird time. Cardiac cycle, electrical conducting, ECG, it's all going to have to go together, I think. If you want to take a mental break right now, take a mental break right now. We're going to start on our new topic, which is the electrical conducting system. All these topics are interrelated. They're all connected. They all connect to the cardiac cycle. Now, I'm going to do this the clinical way first, but I'm going to promise you that there's an easy way to remember this. It's something I came up with in undergrad. Nobody really has a hard time with it after you hear the easy way to do this. Just to remember it, just to remember the order of things. Okay, clinical way first, though, just with the promise that I'm going to make it easy. This is the electrical conducting system of your heart. Just like a motor neuron is going to be innervated, or is going to innervate some skeletal muscle, it's going to have action potentials that release acetylcholine, trigger more action potentials in a muscle cell. So remember, muscle cells are contracting from action potentials. That's true for cardiac muscle cells as well. So here's your cardiac muscle cells, and you have a really, really special system in your heart to convey action potentials. That is your electrical conducting system, or cardiac conduction system, as this slide says. These are modified cardiomyocytes. These are not nervous cells. These, you can think of them about like those T-tubules. They're not T-tubules either. But remember how T-tubules are going to propagate action potentials through your skeletal muscle cells? It's a bit like that. So you have these modified cardiac muscle cells specifically designed to behave like nerve cells and propagate action potentials. That's what we're looking at with this conducting system. We're going to start up here, the sinoatrial node, so SA node, and it refers to its position. Its position right here at the superior vena cava. You know, this is where my superior vena cava is. If my head is my heart, then this is where my superior vena cava is. I don't know. I need a heart model in my hands, and I don't have one at home right now. Okay, here's your SA node. Sinoatrial referring to its position here. And that is your pacemaker of the heart, is what we call it. So this is innervated by your vagus nerve. Your main parasympathetic cranial nerve is coming down to this SA nerve, or SA node. Okay. Vagus innervates your SA node as well as your AV node. I'll get to that in a second. And it moderates your heart rate. Remember, we need your parasympathetic nervous system to be able to lower or raise your heart rate. So, of course, these are both innervated. But the reason this is the pacemaker of your heart is that even without any innervation at all, no nerves coming to your heart, your SA node can propagate its own action potentials. Again, it's a cardiac muscle cell. It's just designed to act like a neuron. It can propagate its own action potentials. Without any vagus nerve stimulation, your SA node wants to beat at 100 beats per minute, which is not ideal. You don't want to be sitting around eating popcorn with a heart rate of 100 beats per minute. That's a bad plan. So that's why your vagus nerve is there to be like, dude, slow down just a bit. Just like 60 to 80 is fine. That's what your vagus nerve is doing here. Okay, so the SA node is the pacemaker of your heart. Wants to fire action potentials at 100 beats per minute. Doesn't, because it's inhibited by the vagus nerve. So all of your electrical impulses spreading across your heart start from the SA node. Signals from the SA node propagate across the atria, and that's going to result in atrial contraction, coordinated atrial contraction. How do those signals propagate across the cardiomyocytes of the atria? Glad you asked. Remember the structure of the cardiomyocyte is that it's a branched cell, right? And at the end of that branch, you've got an intercalated disc with what? That's right, gap junctions. And gap junctions mean that the ionic charge in one cell will be shared with adjacent cells. Oh, it's all coming together now, right? So we have propagation of the action potentials from the SA node, and that spreads through the gap junctions and the intercalated discs across all of the myocardium that is connected. And what we're going to find is that the atria are insulated from the ventricles. We actually have something called the fibrous skeleton. Fibrous skeleton of the heart. And that separates electrically the atria from the ventricles. So we're just going to have a dedicated pathway to get through that insulation. Okay. SA node fires. Action potentials propagate across the atria, causing atrial systole. Signals make it to the AV node, the node located between atria and ventricles on the floor of the right atrium. And we do have this AV bundle. And that makes it through that insulating fibrous skeleton. So what we're actually going to do with that AV node is we're going to delay the action potential slightly. We're going to have a delay here. That means that the atria contract and then the ventricles can contract. We want those to be separate events. We don't want the atria and ventricles contracting at the same time. That's not going to be a good pump. Imagine these pumping all at the same time and all of the valves just going purr. Nothing can move forward in that situation. Atria contract, then ventricles contract because there's a delay at the AV node. We go through the AV bundle. Some sources are going to call this the bundle of His, H-I-S. It's okay. Sometimes I say AV bundle of His, just to be really complete. Make sure no matter which resource you're looking at, you'll get it. The AV bundle branches. We call those bundle branches. Super genius. Big brain time. The bundle branches, right and left, make it to the apex of the heart. At the apex of the heart, they go back up the walls of the ventricles And at that point, we call them Purkinje fibers. Purkinje, 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 Purkinje. I had some very loud students who decided to say it loudly and incorrectly multiple times. And because they did that on the lab practical I had at the time, years ago, everybody in that entire cohort spelled it wrong on the lab practical that I had then. It's not saying it's going to make it onto this lab practical. I don't really know. Ever since then, we're going to do a little follow the bouncing ball, make sure that you can pronounce Purkinje. 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 Okay. I'm having PTSD flashbacks. Okay. Now, the electrical dog's getting up. Electrical conducting pathway. Kamari, you want to show your face? Come. Come here, say hi. Get involved. All right, well, that was an adventure. Okay, yeah, let's keep on moving. So again, now we're getting out of the electrical conducting system and into the ECG. So if you want to pause, take a breather, absorb all of that information before moving on, that's fine. They are interrelated. There's good reason to talk about these things together. So you might remember the graph for an action potential. So we have depolarization, repolarization, hyperpolarization, return to resting membrane potential. It's not the same as this graph. First and foremost, the electrocardiogram is measuring the change in voltage across the entire myocardium in this single waveform. There's different numbers of leads that you can put on a person to detect changes in voltage in more specific areas in the heart. Their typical ECG wave that we're learning today is adding all of those up, adding, subtracting, adding, subtracting, adding, subtracting, all of the electrical changes, every action potential happening across the myocardium, in the atria, in the ventricles, and putting them on one waveform. So this is a summary of all the electrical changes happening across the heart at the same time. Yeah? Yeah. Okay. So it's related to action potentials. It is not a graph of an action potential, nor do these graphs look like each other. We have millivolts on the y-axis, just like you have on your action potential chart. We have time on the x-axis, just like you have on your action potential chart, but this is not one action potential. This is every action potential over the course of one cardiac cycle. So I kept this picture, even though it's a bit old school, because it does tell you some important stuff. So the good news here for this waveform is it is alphabetical. If you know your alphabet, you know that it goes P, Q, R, S, T. Easy peasy, right? This is called the P wave. This big deal right here is called the QRS complex. It's not QRS wave, it's the QRS complex. And this over here is called the T wave. The P wave is detecting the change in voltage while the atria are contracting. The QRS complex is detecting the change in voltage while the ventricles are contracting. The T wave is detecting the change in voltage while the ventricles are relaxing. Now, if you remember your terminology from the action potential, you remember that there's depolarization and repolarization. And if you remember your electrical conducting pathway, you know that these are triggering action potentials. So the SA node fires and causes action potentials to fire across the atria. That means that these cells depolarize. That depolarization causes contraction of the atria. We call that atrial systole. One more time? Yeah, I know you want one more time. P wave correlates with atrial systole. The P wave is the change of voltage detected from the SA node depolarizing the cells of the atria, causing atrial contraction, which we refer to as atrial systole. The P wave is atrial systole. That's what we're getting at here. The QRS complex is ventricular systole. The ventricle is depolarized. But look at everything that controls ventricular depolarization. We've got AV node, AV bundle of his bundle branches, left and right, Purkinje fibers. That all depolarizes on both ventricles, all the way across the walls of the ventricles. Compare that to the electrical events happening in the atria. This is a big deal. So your QRS complex is big. It's complicated, right? It makes sense that it's complicated because we're measuring big changes. And then the ventricles repolarize. So remember your waveform for your action potential: depolarization, repolarization, hyperpolarization. So while those ventricles are repolarizing, that change is detected by a T wave. One question that sometimes gets asked by very smart people is, well, you get atrial depolarization. What about atrial repolarization? It is possible with a certain lead or a certain number of leads to detect atrial repolarization. If you're just looking at one action potential in the atria, then there's going to be a depolarization phase and a repolarization. But this is a summary of all of the action potentials across the heart. So that atrial repolarization phase is caught up somewhere in here, and it's just kind of hidden by this QRS complex. Because remember, we added it all together. I'm going to see if I can find an image that'll help you understand that. This is from Netter's Anatomy Coloring Book, one that I own. I might have left it in Denver. We'll see. At some point, I should probably just check my bookshelves. So this is a great picture. I use this picture literally all the time to convey this idea. So your SA node fires, guess what? You've got depolarization and repolarization. Your atrial muscle depolarizes. You've got a nice little action potential: depolarization, repolarization. Makes it to the AV node, depolarization, repolarization. A little bit of a delay. AV bundle, depolarization, repolarization. So you add all of this together, all of these moments, all of these things that are happening here while the atria contract, or right before the atria contract, you get a little P wave. See how that added together to make a P wave? And likewise, things that start to happen in the ventricles, bundle branches, Purkinje fibers, you add those all together, you get the QRS complex. And then you still have repolarization occurring way down here, but a lot of things have already totally repolarized or in hyperpolarization, so you get a little T wave over here. So this is all we're learning. We're not learning these individually, just this one. Did that help? I hope that helped. Okay, so the three formations of the ECG: the P wave is the impulse across the atria, the QRS complex is the spread of the impulse down the atrial ventricular septum, around the ventricles and the Purkinje fibers. The T is the end of electrical activity, it's the repolarization. The ECG is really useful because if it is something other than normal, then we can detect arrhythmias and things like fibrillation, flutter, any number of blockages in the heart. Blockage is the wrong word. Blocks. There's blockages and then there's blocks and there's different things. But we'll stop there. So for example, you've got a normal ECG recording. You can see your P, you can see your QRS, and you can see your T. You've got some good intervals between each. You can actually use these lines to tell heart rate. The amplitude means something too. We're not doing any of that math in here. This is actually a fairly fast heart rate if these lines are correct. If somebody's gone into a dangerous dysrhythmia like ventricular fibrillation, you're not going to be able to see those specific waves. It's going to look more like that. You can be trained, obviously, to read ECGs in much more detail. If you see a line like this, you can't necessarily automatically go to ventricular fibrillation. That would assume that these are modified QRS complexes. But you can get closer to be able to interpreting EKG results. It's pretty cool. Okay, that was cardiac cycle. That's a good stopping point. I think if there's anything else I want to say. Do you want to do a quick summary? Let's do a quick summary. This is what I do in an A&P level class. So while you're here, you can learn each of these things distinctly. You can learn the electrical conducting system on its own. You can learn the ECG on its own. You can learn cardiac cycle on its own, and that's fine for now. In A&P, this is what I'm going to do to you. Atrial systole begins. The AV valves are open, the semilunar valves are closed. There's a slight increase in pressure in the atria. The SA node causes atrial depolarization and is detected by the P wave. Early ventricular systole. We're going to close the AV valves, allowing for the increase in pressure in the ventricles. The start of ventricular depolarization is detected by the QRS complex, and it is caused by the AV node propagating action potentials down the AV bundle of His, down the bundle branches to the Purkinje fibers, and that works, the electrical works for both early and late ventricular systole. In late ventricular systole, the pressure in the ventricles has overcome the resistance in the great vessels, opening the semilunar valves, causing ejection and the maximum amount of pressure in both the ventricles and in the aorta. The AV valves remain closed. This again was detected by the QRS complex and propagated action potentials through those bundle branches and Purkinje fibers. Then we have depolarization in early ventricular diastole. Early ventricular diastole closes the semilunar valves when back pressure from the aorta and some pulmonary trunk slam the semilunar valves closed, causing a slight increase in pressure in the aorta, causing a detection of something known as the dicrotic notch. Now this is repolarization, so this is the end of action potentials. So that's actually going to be detected by a T wave, but everything in the electrical conducting system is actually repolarizing at this point, leading to isovolumetric relaxation, ventricular and atrial diastole. Feel free to get there now. If you can't, don't. Just learning each of these things individually means it's going to be easier for you to connect them all up later.